Stable view synthesis is a new method that synthesizes spatially and temporally coherent photorealistic views of complex real-world scenes. Here is a novel trajectory through a scene from the tanks and temples dataset synthesized by our method. Stable view synthesis works better than recent state-of-the-art approaches to novel view synthesis. Images synthesized by our method are sharp and photorealistic. They are also spatially and temporally coherent and avoid gross artifacts that can plague other techniques. Our method aggregates feature vectors projected from the source images directly on a 3D scaffold of the scene. To construct the geometric scaffold, we use structure from motion, multi-view stereo, and surface reconstruction. Each source image of the scene is encoded by a convolutional network to produce a tensor of features. The core of our method is the aggregation of these features directly on the 3D scaffold of the scene. At each point on the scaffold, feature vectors are projected from all source images at which this point is visible. These projection directions are shown in green. A differentiable deep-set network is then used to aggregate these projected features and produce a new feature vector in the direction of the target view, shown in red. The target view is then rendered by a convolutional network from a tensor of features synthesized in this way for all pixels. How do we compute a view-dependent feature vector for a given 3D point X on the surface, denoted as gamma? First, we compute the ray U from the 3D point X to the target view. Second, we identify and aggregate all directional source image features that map to the 3D point X. The result of this aggregation is the target feature vector G that is projected into the target view. The differentiable deep-set network, phi, takes into account the target view direction U, the source view directions, and the feature vectors from the source images to produce a new feature vector G in the direction of the target view. Let's compare our method to recent state-of-the-art view synthesis techniques on a number of real-world scenes. First, we compare to neural radiance fields ++, a recent method that fits multi-layer perceptrons to represent the 5D radiance field and uses volume rendering techniques to synthesize images. We observe that the results of NeRF++ are not as sharp as our results. Next, we compare our method to neural point-based graphics, or NPBG. This technique fits feature vectors to 3D points in the scene and renders these via a convolutional network. We see that images synthesized by NPBG are sometimes corrupted by black blob artifacts. We now compare our method to free view synthesis, or FVS, a recent approach that maps a selection of encoded source images into the target view and blends them via a recurrent convolutional network. While FVS utilizes the same geometric scaffold as our method, it sometimes exhibits gross localized artifacts due to incomplete coverage of the scene by the selected source images. Let's compare the methods on the truck scene from the tanks and temples dataset. We begin again with a comparison to NeRF++. We proceed to a comparison with NPBG on this scene. We can again see that our results are crisper, more photographic in appearance, and more stable. Free view synthesis exhibits artifacts in this scene as well, for example, on the bed of the truck and at the very left of the image. In contrast, our results are crisp, complete, and temporally stable. Let's take a look at another scene, this time from the FreeView synthesis dataset. We can again see that images synthesized by our method are clearer and more detailed than NeRF++. Likewise here in the comparison with NPBG. The NPBG images are blurrier and also suffer from some shimmering and black blob artifacts. FVS suffers from severe failures on this scene due to the selection of source images. From one frame to the next, the results of FVS can suddenly change when the set of source images selected by that technique changes. In contrast, our method utilizes all available information at all times and is inherently stable by design. Thank you for your attention, and please refer to our paper for details and quantitative results.